Hi, I'm Kwang, and today I'll be talking about learning to assign orientations to feature points. And as we all know, local features are a core building block of computer vision in various tasks, including image matching. And normally, given an image, you have three steps, where the first step is the feature detection, and the second step is the orientation estimation, and third, you extract the descriptors. And if you look at what's been done for the first and the third, there has been numerous work really, and if you take a look at what's been done for the second part, actually, there's almost nothing. And the reality here is that we still rely on the heuristics that the early method suggested, which is not really ideal because this is actually a very important step in the local featured pipeline, but it's largely overlooked. And before we go any further, I want to remind you what orientations are. So orientations are a tool for aligning patches across different images before you extract the descriptors. So given, for example, in these two patches, if you use the dominant gradient orientation of Swift, which is kind of like the de facto standard nowadays, you get something like this, in which the gradient changes. But so that they're aligned, and then extract the descriptor problem because you have these errors in the orientation. The computer vision problem, I want to show you a multi-view get with dominant gradient orientations, and you can and this is mainly due to the fact that the errors, like on the bottom, you're gonna have errors. On the other hand, you get something important in using local features. On heuristics, or rather, which the good orientations for matching. And to do that, we first need a definition on what good orientations are. And in fact, for a single patch, there is no. What I mean by that is like this one or the other one is actually that we want are extracted on the same physical point. A more tight rim with the ultimate is the final descriptors to be consistent. So we keep this in mind, and when we formulate our learning problem, we between the pairs of training samples. But with a twist. So as you would normally do in case of Siamese, that distinguisher method. We do this because we want pipeline, and to do that we use numerical, and this allows us to even use and the second problem, they are periodic, and this is a major problem. Return to the same value. So in I propose to learn two alpha values followed by a nice differentiable way of architecture we use is quite standard and simple, and two fully connected layers. And while this configuration already works quite well, we wanted to push things a little further, so we introduced a new type of activation function for the fully connected layers. The new activation function we propose is called what we call generalized hinging hyperplanes, or simply GHH. It's actually a generalization of the popular ReLU, PReLU, and max out activations. What these three activations on the top have in common is that they're piecewise linear, and actually the generalized hinging hyperplane activation we propose is a general form for any piecewise linear function. So in fact, it's more powerful and flexible in what it can describe. And not surprisingly, the activation function we propose works the best for estimating orientations. So for evaluation, we pretty much try to use all the data sets we can have our hands on, including one of our own. And we use the standard Oxford data set for training, as it has various imaging changes, including illumination and viewpoints and etc. But one thing I want to emphasize here is that we train only for the Oxford dataset and test in all the others without any retraining or fine-tuning. And we use the descriptor matching performances for evaluation, as in fact we're interested in orientations that improve the descriptor matching performances. And we compared it with 12 other competitors, including 3 rotation invariant ones, to show you that indeed orientations matter. So to start with, we compared using the H4C key point detector and the SIFT descriptor combination, and this is the result on all the data set in average in terms of mean average precision. Mean average precision is basically the area under curve on the precision recall graph, and higher is better. On the left is the one with the original heuristics used for the orientation estimation, and on the right is our learned orientations with the Rattler activation function. And you can already see that there is a significant improvement in terms of mean average precision here. And if you use the generalized hinging hyperplane activations, you get a little bit further. And this not only holds for the H4C and the SIFT descriptor combination, but actually all the key point detector and descriptor combinations we tried. And that includes the Oxford Visual Geometry Group's learned descriptor here, which shows very high performance compared to SIFT. And if we compare the best results we can get with all the other methods that use heuristics based for the orientation estimation, you can see that we have a significant improvement. And this holds for the case when we use our orientations with the handcrafted one and also the learned one here. And the thing is, you can basically benefit from our improved matching scores for basically all the applications that involve local features. And this is a homography estimation result between the two images here. And the green boxes show the homography estimation results. And you can see that the results on the top with our orientations are more accurate than the one below, which is the dominant gradient orientation. And the changes can be quite subtle as shown here, or a bit more as the one shown here. But it can also be drastic as the one shown here. And it's quite impressive that such a small change in the local feature pipeline actually leads to this kind of drastic difference. And if we go back to the multi-view stereo example, even a sophisticated pipeline such as the multi-view stereo pipeline can really benefit from having better orientations. For example, the building on the back here, in the two left examples where the heuristics are used, you can see that it's almost not recovered, whereas on the right, with our learned orientations, you can recover them. And this is another example. If you look at the face of the doll on the left, you can really see the difference between the using heuristics and our learned orientations. So these are just a few examples of what you can really do by enhancing the orientation assignment part of the local features. And to sum it up, orientations are really a key component in the local feature pipeline that has been largely overlooked. We proposed a deep learning-based approach that learns these orientations implicitly and discovering what are good orientations for matching. And for further performance gain, we proposed to use a new activation function called GHH. And finally, it was really exciting to see that orientations do matter in a lot of cases. So we have the source code and the datasets not yet, but will be up soon. And thank you for your attention.